Hey guys, welcome back to Code Crusaders. Today we're solving LeetCode 1356, sort integers by the number of 1 bits. It's marked easy, and it's a great problem to understand custom sorting properly. So let's break it down step by step. The problem gives us an array of integers, and we need to sort them, but not by their value. Instead, we sort them by how many 1 bits they have in their binary representation. For example, the number 3 in binary is 0011. That has 2 1 bits. The number 5 in binary is 0101. That also has 2 1 bits. Now here's the important part. If two numbers have the same number of 1 bits, then we sort them normally in ascending order. So basically, it's a 2-level sorting rule. Let's take the example input, 0, 1, 2, 3, 4, 5, 6, 7, 8. First, we convert each number into binary and count how many ones it has. 0 has 0 ones, 1 has 1 1, 2 has 1 1, 3 has 2 ones, 4 has 1 1, 5 has 2 ones, 6 has 2 ones, 7 has 3 ones, 8 has 1 1. Now we group them based on the count. Numbers with 0 ones, just 0. Numbers with 1 1, 1, 2, 4, 8. Numbers with 2 ones, 3, 5, 6. Numbers with 3 ones, 7. Now within each group we sort by the actual value. So the final answer becomes 0, 1, 2, 4, 8, 3, 5, 6, 7. Now let's talk about the pattern. Whenever you see sort by some custom rule along with a tie-breaking condition, that's a clear signal. This is a custom comparator problem. In Python, this becomes very clean because we can use a sort key. The trick is returning a tuple as the key. The first value in the tuple is your primary rule. The second value is your secondary rule. Python compares tuples from left to right. So it first compares the bit count. If those are equal, it compares the number itself. So for this problem, the key for each number is simply bit count, comma, the number. Now how do we count 1 bits? In Python, the easiest way is using bin of n and then counting how many times the character 1 appears. So bin converts the number into a binary string and count tells us how many ones are there. Very readable and direct. So the Python solution returns the sorted array with a lambda that gives us a tuple. First the bit count, then the number. Let's simulate how sorting actually happens. Suppose we take the number 3. Its bit count is 2, so its key becomes 2, 3. Suppose we take the number 4. Its bit count is 1, so its key becomes 1, 4. Now imagine the entire array being transformed into these keys. Python sorts these tuples lexicographically. First by the first element, and if they're equal, by the second. So numbers automatically get grouped by bit count, and inside each group, sorted by value. We didn't manually group anything. We just defined the sorting rule clearly. If you're using Java, the logic is exactly the same, just different syntax. You use arrays.sort with a comparator. Inside it, you compute the bit count of both numbers. If the bit counts are different, return their difference. If they are equal, return the difference of the numbers. Same idea in C++ using a lambda and the built-in popcount function. Across all languages, the idea stays the same, custom comparator with 2-level comparison. Now let's quickly talk about complexity. Sorting takes n log n time. For each element, we count bits. Technically, that depends on the number of bits in the number, which is log base 2 of the value. But the maximum value here is 10,000, which is around 14 bits. So bit counting is practically constant. So overall time complexity is O of n log n. Space complexity in Python is O of n because sorted creates a new list. In languages with in-place sort like C++, extra space is mostly recursion stack, around log n. Let's summarize the full logic clearly. Convert each number to binary. Count its 1 bits. Sort using a tuple key, first by bit count, then by value. Return the sorted result. Whenever you see sort by custom rule with tie breaking, think tuple key or custom comparator. That's the pattern. And that's it for today. If this helped you understand custom sorting better, keep practicing. You're building strong interview intuition. See you tomorrow.